All right, so here again is the iteration formula that defines Newton's method. And one criticism we could make of this formula is that in order to go from xn to xn plus 1, I have to know not only the original function f of x, which helps define my problem, after all, but I also have to know f prime and be able to calculate f prime at a point. So that means that, from whatever problem I start from, I have to take a derivative to find f prime, and then I have to code that up. And you might remember that when you have an expression, usually when you take the derivative, the expression gets longer. So that's a bit annoying. Another fact is that means that there are two separate functions that we're calling at each iteration. We're calling something to evaluate f, and we're calling something to evaluate f prime. So that may seem like a pretty minor objection, but in realistic problems, you might not have a simple formula to evaluate for f. F might represent, for example, the solution of a differential equation or a particularly difficult integral. And in that case, you really don't want to either have to figure out what f prime is, and you certainly don't want to have to make more calls to evaluate expensive things than you absolutely need to. So for both of those reasons, it's desirable to find an alternative formula that doesn't make this requirement on us. So to do that, we're going to go back to the main idea. So remember, in Newton, the main idea was to use a linearization of the function. So a linearization as defined in calculus. And then, that's like a linear model of the true function, and we solve the model to get the next value for the iteration. Well, let's suppose now we have not just one previous point, but two. So what we can do is we can use the fact that f prime represents a slope, right, dy dx, and we can replace that with delta y over delta x. Okay, so instead of the tangent slope, we're using an approximation to that slope, but it's one that doesn't require us to know what the derivative is. Okay, so graphically, right, here's the original setup we had. The blue curve is y equals f of x, the true thing that we're trying to find a root of. The red line is the tangent line. That's the one that we get from linearization, and it's the one we solve to derive Newton's method. But now let's suppose we also have another old value, xn minus 1, which means we have another point on the curve. Okay, and we can draw a line through those points. Okay, so the terminology for this is a secant line. It's a line that goes through 2 points on the curve. And that's a different kind of linear approximation of f. And as you can see, we can still solve it. We get a different approximation to the root. So because of this, we call it the secant method. Here it is. We solve our secant line model. So, right, we said that formula was right up here. Okay, that's our formula. So we plug x equals xn, or x equals xn plus 1 at the new value, and then set it equal to 0. And then that gives us this formula, which we rearrange to get xn plus 1 in terms of the previous two guesses. So this is the secant method. Iteration formula. And this idea is often called a quasi-Newton method. We take the Newton idea, but we modify it somewhat so that we don't have to use the exact value for the derivative. Okay, so because of the n and the n minus 1 in this formula, we have to start at n equals 1. okay, which means we need x0 and x1 in order to get started. So at n equals 1, you plug those two into the right side, and out comes x2 on the left. And then x1 and x2 give you x3, and so on. Okay, now one thing to note about this is that it looks like we haven't improved things in terms of the number of function calls, because in order to go from xn to xn plus 1, I have two calls of f appearing in the formula, f of xn and f of xn minus 1. However, so think about the case when n is equal to 3, let's say. So that means we need f of x3 and f of x2. But we already had f of x2 when we computed x3. So maybe it would help if I write this out. Oops. Okay, so first we would have said that x3 is equal to x2 minus x2 minus x1 f of x2 divided by f of x2 minus f of x1. So that would be the case where n is equal to 2. Okay, then we increase n. So we found x3. Now we want to find x4. So we put in n equals 3 everywhere into that formula. We have that. Okay, so this is running inside some kind of a for loop. Well, if you just look at the expression on its own, it looks like we have to call f twice. And if we're lazy, that's what we'll end up doing. But if we're smart, right, you'll notice that the f of x2 that I need here is something I already had to compute up here in the previous iteration. So there's no need to recompute it. All I have to do is remember it from one iteration to the next. So I have to keep that one value from one iteration of the loop to the next, and then I really only have to make one new call to f per iteration. And so that should save us some work if f takes a long time to evaluate. Okay, so here's an example of the formula in action. We have two initial guesses, x0 is equal to 2 and x1 is equal to 4. This is the same polynomial as in the Newton's method lecture, so it has a root at x equals 3. Okay, so we'll write down the formula for x2. Whoops, that belongs in the denominator, not the numerator. Okay, so we'll tabulate the things that we need here. F of x0 is 4 minus 3. F of x1 is 16 minus 8 minus 3, so that's 5. Okay, so that means that x2 is equal to 4 minus 2 here, 5 here, and let's see, this should be a 0. I'm not sure, just didn't write correctly. This is 5 plus 3. So I get 4 minus 10 over 8. So that's 15 over 4. Oh, sorry, that's 11 over 4. Okay, so that's the end of the first iteration. Now in the next iteration, I'm going to use the fact that x3 is x2 minus x1 times f of x2 over f of x2 minus f of x1. So now I need to compute f of x2. I have to go back up to where f is there. So it's 121 over 16 minus 11 over 2, which is 88 over 16, minus 48 over 16. So we have we have 33 minus 48, negative 15 over 16. Okay, so this is what I'm talking about. I already have f of x1 from above. I don't have to compute that again. So now we can compute x3 as 11 fourths minus, let's see, where did x2 go? x2 is 11 fourths minus x1, which was 4. Times f of x2 divided by f of x2 minus f of x1. And I think I'm getting a little tired of pushing all these fractions around, so you can evaluate that numerically, and so on. Okay. So let's talk about the convergence of this method. We can analyze it in pretty much the same way as Newton's method, but then there's a twist. So we start with the iteration formula, and then we define again the error as the difference between the algorithm's value and the true root. So you subtract r from both sides of the formula, and then you substitute in for xn and xn minus 1, getting rid of those in favor of the r's and the e's. Right? So this formula leads directly to that one from substitution. And now we have the same idea as we had before. Supposing that the sequence is converging, the errors should be getting small. If the errors are small, we can do Taylor expansions. We do the expansions in a bunch of algebra, and a while later we get the following expression. And you see it's awfully close to the Newton case. Remember, in the Newton case we said en plus 1 was this same constant times en squared. So now instead of en squared, I have en times en minus 1. And since the n minus 1 error probably isn't as small as the nth error, this isn't going to be quite as small. In other words, it's going to converge a little bit more slowly than Newton's method does. Well, this is a slightly more difficult kind of recursion to solve for. The details are shown in the book of how to do it, but the conclusion is that the ratio of en plus 1 to en to a power alpha goes to a constant in the limit as the sequence converges. And that constant is actually the golden ratio, 1 plus root 5 over 2 exactly, or about 1.62. Okay, so in this ratio here, right, alpha equals 1 would be linear convergence. alpha equals 2 is quadratic. Oops, quadratic. But what we have here is alpha's in between. So this convergence is faster than linear, not as fast as quadratic. We call it superlinear. Okay, so that's the price that we paid for not using the exact slope. Okay, but there's one last twist to the comparison. So if we compare Newton and secant, right, well, we'd say, well, in one iteration of Newton, we go from en to en squared in the error. In one iteration of secant, we go from en to the 1.62 power, right, which doesn't go to 0 as quickly. It's not as small when en is a small number. But remember that Newton requires us to call both f and f prime for each iteration. Secant only requires us to make one call to f in an iteration. So if we did them on an equal cost basis, if we were allowed to take 2 iterations of secant, to take 2 function calls, then you find that you take the error to the 1.62 power, and then you take it to the 1.62 power again, and the result is actually smaller than the Newton error. So it depends on how you measure. If you measure by the iteration numbers, Newton's going to converge faster. But if you go by sort of an equal cost basis, the secant method actually converges faster.